All right. Good afternoon, everyone. So my name is Sid Raskar. I'm a postdoctoral appointee in data science group at ALCF. And today I'll be just giving you an overview of the AI test beds that we have here at Argonne. So let's get started. So before we get into all the AI accelerators that we have at Argonne, first I would like to give brief introduction about why we need AI accelerators. So as we know, like the traditional architectures pretty much look something like this, where we have a bunch of cores, which is our CPU, and it's connected with your DRAM, your central memory, and instructions and data is fetched from this uh, memory to the cores, and this kind of architecture leads to very heavy data movements, which add to the energy costs, which is one of the reasons GPUs and CPUs are so energy hungry. And to tackle this very problem, we are now moving towards domain-specific data flow inspired architectures. And if not all, most of them pretty much look like this, where you have uh, cores and memory together on chip, and data kind of flows through them to generate the results. So that's the main motivation behind moving towards domain-specific AI accelerators, and this is the main characteristic of these architectures. Uh, the workflow to get your program executed on this AI accelerator is can be summarized like this, where you represent your program in terms of a graph, and then you have compilers which map this graph onto these architectures, and then these graphs are executed. So all these architectures have their own software stack to support pretty much the similar workflow. So now, like AI test beds at Argonne. So this is very important website. You can go here and check out what all AI test beds we have at Argonne, and how like some documentation about that is available on this website. So the general idea behind having AI test beds at Argonne is to have this infrastructure where we can test out various AI applications on these test beds, see how they perform in comparison to traditional CPUs and also with GPUs. And going forward, the goal is to integrate these architectures in the future supercomputers, and try to understand how future supercomputers can look with these kind of AI testbeds. So that's the main motivation behind having this AI testbed program at Argonne. So now let's get ahead, and like this is the so at Argonne we have these four AI testbeds at this moment. They are from Cerebrus, Sambanova, Graphcore, and Grop. So for these four test beds, I'll be talking about, I'll be giving like very brief introduction about their architecture, some salient features of each of them, then what applications we have been able to port to these architectures, and like few early publications that we have regarding these architectures. So let's start first with the architectures, and then first with the Cerebrus. So Cerebrus, the novelty about Cerebrus architecture is like their wafer scale architecture. So here in this diagram, like entire chip of Cerebrus is compared with the largest GPU out there. So what they're trying to do is come up with the super huge chip, which is at wafer scale, and then they map your program to this chip. So this is how the unit of Cerebrus systems looks like, which hosts this chip. And just to give you some ideas about the numbers, this chip consists of 400,000 cores, and each of that core has and 18 GBs of on-chip memory is spread across these 400,000 cores. And here are some numbers about the bandwidth. So this chip is constructed with 60 nanometer process, and this is the first chip, like CS1, and it has about 1.2 trillion transistors. So the other part of this any AI architecture, like other than the architecture, is the software, which the software toolchain, which helps you to map your programs to these architectures. So Cerebrus, at top, you write your code in like these are the claim framework support from Cerebrus. So you can write your code in PyTorch, TensorFlow, etc. And then they have some intermediate representation, which is called as linear algebra intermediate representation. And then the compiler takes this information and maps your program onto the on this huge chip, and then it's executed. So this chip this chip supports both training as well as inference. So that's, if you want to find more information about this architecture, you can visit Cerebrus website or this Cerebrus white paper, which is available for everyone. Next, we'll talk about Sambanova. So Sambanova's architecture, it's also like similar in the sense that you have a bunch of compute units and memory on the chip. So Sambanova has this cardinal SN10 chip. This is how the die looks like, the picture of it. And inside it, it comprises of this memory, pattern compute units and pattern memory units, and all these units are connected through switch, and data basically flows through it. And they call this architecture as reconfigurable data flow unit architecture. So not as much as Cerebrus, but this chip also has about 100 megabytes of on-chip memory spread across all these pattern memory units. It consists of 400 billion transistors, and it uses 7 nanometer process for its constructions. And the claim performance for this is hundreds of teraflops. And then here in this diagram, we have the software stack. So this is what they claim to support, which is used to, like, again, map your program written in TensorFlow, PyTorch, and other frameworks to the actual chip through all these compiler tool chains. So again, this chip is also can be used for training as well as inference. Now, the third architecture that we have here is Grop, and their processor is called as tensor streaming processor, and this is like generalized block diagram for this tensor streaming processor. The interesting fact about this architecture is that this architecture is tuned for inference only, unlike the earlier two architectures. And I couldn't talk about like the software stack for this, but we can say that it also supports TensorFlow and PyTorch. So this architecture also has about 220 megabytes of on-chip memory. It uses 14 nanometer process, and it consists of 26.8 billion transistors. And they claim up to 1 petaflops of performance in integer 8. So this is the general architecture of tensor streaming processor. And just to give you further idea, like they have like two hemispheres here, west hemisphere and east hemisphere, and the program is mapped on this architecture so that the data flows to west and east through these hemispheres. Next, I'll similarly give brief overview about Graphcore's architecture. So they call it Colossal MK2 Intelligent Processing Unit. Similar to earlier architectures, it has about 900 megabytes of on-chip memory, and it also has these IPU cores, and they are put together in these IPU tiles, and the memory, 900 megabytes of memory, is spread across the chip. Again, similar to the earlier architectures. So Graphcore has claimed performance of 250 teraflops in FP16, and they also support TensorFlow, PyTorch, and in addition, they have their own software stack, which they call PopArt. And this architecture it supports both training and inference. And this is how the software stack of Graphcore looks like. So on top, you have support for TensorFlow or PyTorch, and then they have their compiler tool chain to get those codes mapped onto the actual systems. So that was the brief like introduction about the architectures. Now we'll talk about the applications that like various groups and people in Argonne are working on porting to these architectures. So for Cerebrus CS1, like there is work going on to port these various applications from cancer drug response to protein folding to gravitational waves, which are using Cerebrus CS1 system. Next, for Sambanova, there is work going on all these applications to port these applications on Sambanova's system. This is just a list of those applications. And like I don't have information, like I cannot share information about Graphcore and Grok yet. And for publications, like we have this one publication, Accelerating Scientific Applications with Sambanova RDA. So that's the only publication so far. So that's all I had, like just a quick overview of various AI testbeds at Argonne. Thank you.